I'm going to tell you about two very interesting. This is a rather simple process compared to, for example, how the Appalachians were formed and wore down. This is going to tell you about two plate tectonic events. One from the deepest part of the Earth, the Marianas Trench, and the other on the San Andreas Fault. Fairly relevant, the latter one. The Marianas Trench. As some of you might know, many of you from just reading the news in the past 6 months, that someone, what's his name, Cameron, just went down there. It's the deepest valley on the ocean floor. The trench was created by subducting plates, the Philippine again.
Subduction occurs where two tectonic plates collide. As they grind past each other, the heavier plate is pushed beneath the lighter plate. The descending plate is forced down into the Earth's intensely hot interior called the mantle. It takes with it water and sediment built up over millions of years. As the descending plate dives down, it digs into the mantle. Here, the colliding plates form a trench, a giant crease in the ocean floor.
Normally, subducting plates will produce earthquakes, like the Japanese earthquake. But no earthquake occurs along the Marianas Islands, which is very unusual. And I'm going to give you a little of the geochemistry behind that. Why, if that kind of grinding creates earthquakes in most places, doesn't it happen here?
But the Marianas Trench, the deepest subduction zone in the world, hasn't caused a devastating earthquake since records began in the 17th century. Investigators needed to know why. They hoped the trench's shallower western edge might provide the answer. Here they found an intriguing chain of underwater hills 2 miles below the surface of the sea. Engineers drilled down into the hills and collected core samples. The fine powdery mud is made up of a soft type of rock that has been ground up in the subduction zone.
An unusual kind of mud in the Marianas is made out of serpentine. And serpentine is a very weak rock, and it can be scratched with a knife or something like that.
Investigators realized the grinding plates crush the soft rock to form a lubricating mud that prevents large earthquakes.
Well, that's not an isolated case. As you'll see, a very similar tribological process is taking place on the San Andreas Fault. So here, the place, again, by doing chemical analysis, they discovered very low friction rocks, and they associate that with creeping instead of quake-type stick-slip events. How about the San Andreas Fault?
The San Andreas Fault is one of the most dangerous geological features on Earth. Since records began, there have been 13 large earthquakes along the San Andreas Fault.
The water lines have ruptured. There is no water coming out of the fire.
Before the earthquake, it was a solid boundary fence dividing two fields. But when he recreated what had happened, Lawson realized that the land had jolted apart and torn the fence in two.
That's what's typical about the motion of the San Andreas Fault. But there's an exception.
The small town of Hollister is unique along the San Andreas Fault system. It's never had an earthquake, plenty of clues suggesting that the land must be moving here, and walls that are bent out of shape. But then, the investigation moved 100 miles south to another small community where the land also creeps along. The movement here around the bridge is strikingly similar to the slow creeping ground of Hollister.
And you know, the San Andreas comes off the flank of that hill and right across that field, right under the bridge, and then right over by the corner of that building or that fence post, and then on off to Middle Mountain.
What we're looking at here are cores from the active San Andreas Fault from a depth of about 2 miles. So for the earth science community, these are like moon rocks.
Buried within the rock cores, they found a vital clue about the way that land slips along the San Andreas. They found serpentinite.
The reason that serpentinite is so interesting is that serpentinite is very easily altered to talc. It allows the rock to slide at very low force levels. Talcum powder is very slippery.
Talc's crystalline structure of soft, sliding, flat plates makes it one of the slipperiest rocks known to science.
In Central California, we see that the secret of the slipping San Andreas Fault is actually the rocks themselves.
For those of you who can't quite grasp something as large as core samples and analysis, think of fib analysis of surfaces in TEM and you'll get the picture. All right, just to give you a background, serpentinite is a rock that's composed of one or more serpentine group materials. These materials have this composition, and there are various reactions by which serpentine minerals can become talc. There's a whole class of these materials that are known to be very slippery. There's a lot of triboscience that is now being done on these. People have gotten fault samples from that episode that you saw there. I think that was taken back in 2005. A lot of work has been done to identify the materials involved. Geochemists do this. There's been quite a bit of tribology done on that. The kinds of studies in the temperature range at which the faults may be moving. Work by Terry Tullis's group, who many of you know, showing that if you move at a certain speed, you get something that he calls flash weakening, where the friction drops. And these are the speeds at which faults are expected to be moving very slowly, of course. One of the interesting things, and this got me thinking about it, is reading a paper where they simply put the material in and they find that they've got to have at least 50% of the minerals to get the low friction. And I'm thinking, you know, this is a problem we always deal with. Do you really need the bulk material to get the low friction, or could we be dealing with the third body problem? And so these are the kinds of questions that I would ask the geochemists. If indeed there is some kind of third body forming, you may not need 50%. You may, during the sliding process, bring the more slippery material, which is being converted here in the fault, to the surface. So you may not need 50%. That's because that's not recognizing the third body issue. I would also think that the techniques that we've been talking about here, in situ sliding and using Raman spectroscopy, it wouldn't be too hard to build a chamber in which one could do in situ analysis, watching what's going on with these minerals, having the Raman there, and discovering what's going on at the interface, whether tribochemical films are being formed. And I just did some literature research, and it turns out that most of the exciting spectra, most of the materials that you get Raman spectra from, are indeed minerals. These minerals are quite complex, and there's a lot of Raman spectroscopy. So I could see that as a nice approach. All right, so what are my future plans? On Wednesday, my wife and I are going out for a week, and I look forward to taking a trip up the coastline with my new favorite friend, which is called the Roadside Geology, to northern and central California. Anyway, it's been a real trip being a tribologist. I feel like I'm still doing it, and I hope that you all have as fun a career in science as I did. Thank you.